Okay guys, we're going to do some water quality sampling, and to get started we're going to do nitrate first. So nitrate, this is our instructions. Let's see here. Okay. All right, so we are going to, I'm going to leave this here, and we are going to begin that test. Okay, so it says that I need to fill the test tube to 5. So it's always a good rule of thumb to fill it up with your sample, shake it. You should do that 3 times. I've already done that once, so that would have been my third, to make sure that you have a pure sample. I'm going to fill it to the 5 line. So here we are at 5. Okay, and now I'm going to put in nitrate 1. Alright, and I need to mix until this tablet has disintegrated. That'll take just a second. You really should try to refrain from doing that one and do like an inversion, so that way everything is dissolving at the same rate. Alright, so it looks like that's pretty much dissolved. I'm now going to add a nitrate 2, and then I'm going to put it in its sleeve. So here's the sleeve, and here's nitrate 2. Alright. Alright, and it wants us to mix this for 2 minutes. So it's time. So nitrogen is a nutrient that acts as a fertilizer for aquatic plants. When nutrient levels are high, excessive plant and algae growth creates water quality problems. Nitrogen enters the water from human and animal waste, decomposing organic matter, and lawn and crop fertilizer runoff. Nitrogen occurs in water as nitrate, or NO3, nitrite, NO2, and ammonia, NH3. Unpolluted waters usually have a nitrate level below 4 ppm. Nitrate levels above 40 are considered unsafe for drinking water. So we would really like for this sample, hopefully, if it's unpolluted, it'll be below 4 ppm. But note that this video was taken in November, November the 10th. We are in East Tennessee, right? So deciduous forest, there was quite a bit of leaf litter present at our test site. And if we look at the, if we look at the video, or if we look at the time here, it's been about 2 minutes. So we're going to let the nitrate sit and wait for a whole 5 minutes. Okay. All right, so we're going to move on to our next sample here, which is going to be phosphate. All right, so phosphate is what's up next. Maybe it'll focus a little bit better on the paper. All right, that's okay. I'll read it. All right, so looking at phosphate, these have already been cleaned as well in my previous attempts. So according to our instructions here, it gets worse, okay. We're going to fill the test tube to the 5 ml line. Okay. We're going to add 1 tablet, and then we're going to mix it until that tube has disintegrated, and then wait 5 minutes. Okay. So this test tube has already been cleaned. Like I said, I'd already cleaned this earlier in my test run for this video. Oops. far. Okay. Then we're just going to pop one tab for this one. Note that these tests can also be done in a different chemical method. This is kind of like the rapid test, right? So we're going to mix it until it disintegrates. Like you can do these in like different kits. So we actually have one of the test kits that we're going to do both the tab and we're going to do it like with the actual chemicals. Traditional learners did both, but this way it's just much more rapid results. And this is something that like you could do at home. So like if you go to Amazon, you can actually get these test kits. And you can test any like water sample in nature. Water samples in nature versus the ones like at your house for like drinking water are going to be different. Okay. All right, and as I'm mixing this phosphate, let's take a look at this. Phosphate is a nutrient that acts as a fertilizer for aquatic plants. When nutrient levels are high, excessive plant and algae growth creates water quality problems. Phosphorus occurs in natural waters in the form of phosphates, or PO4, with over half of the phosphates in lakes, streams, and rivers coming from detergents. Phosphate levels higher than 0.03 ppm contribute to an increased plant growth. All right. Hopefully, we're almost there on the disintegration. All right. That is pretty disintegrated. All right. And boom, disintegrated. All right, so we're going to wait 5 minutes on that one. Now if we come back to this, 5, 6, 7, 8, we have about 1 more minute left on our nitrate one. So while we're waiting on that one, I thought I would tell you a little bit about one of our other tests. So we're going to be doing 2 different tests. We're going to be doing chloroform or bacteria testing. We didn't do that one today, but there's a few different ways you can do that one, but we're testing for chloroform and E. coli. But there's also a turbidity test, and we have a giant tube for that that we use that's like 6 feet tall. You can do smaller samples as well, but I no longer have that jar. So what these black and white things are called, they're called Siki discs. And basically you take a sample of water and you hold it above there and you let it out until you can't see it anymore. And then once you see that value, that's how many particulates in that suspended column would be in the way. That's why you can't see the bottom of the lake, right? You have so many different particles. And so you'd be able to tell the turbidity there. So that's all we have for turbidity for this video. But we will be testing for it later. Okay. So at this point, we're ready for our nitrate. Let's bring it back up. Okay. Here we have our sample. And if we match it up, you determine what value do you think it is. Are we at 5? Are we at 0? Would you consider us less or more? Okay. All right. Well, if you've got that calculation, note that it says that below 4 is unpolluted waters with above 4 contributing to some pollution. Now, if we were outside in the field, you can throw this not directly into the water, but you would throw it where where there's like a bunch of vegetation, so that way the plants can absorb any of the chemicals. But we're just going to wash it down the sink to ensure that with extra water, just to make sure that it isn't doing anything to our systems. Okay, so that is nitrate. All right, at this point, we're ready for phosphate. So we're going to bring that back out. All right. And if we look at the phosphate chart here, we have our sample. All right, so it's 1, 2, 3, 4. And you determine what you think it is, but remember that higher than 3 could contribute to increased plant growth. Okay. All right, so we're going to move along. I'll empty that later. Let's take a look at our pH. All right, so here is our indicators. All right, and here's a little bit about pH. It's one of the most common analysis that we have in water testing. It's a measurement of the activity of hydrogen ions. In a water sample, the pH scale ranges from 0 to 14. Water samples below 7 are considered acidic, and those above 7 are basic, with 7 being neutral. The pH ranges of 6.5 to 8.2 is optimal for most organisms. Rapidly growing algae and vegetation remove carbon dioxide from the water during photosynthesis. This results in a significant increase in pH. Most natural waters have a pH of 5.5 to 6. Alkaline soils and minerals can raise the pH to 8 to 8.5, with seawater having close to an 8. So this was just from a stream, so it might not be anything like that. All right, so we're going to fill the test tube to the 10 ml line. Oops, a little too far. All right, perfect. So we're at the 10 ml line, and we're going to add just one of the pH tabs there. Beautiful. Okay, and we're going to cap it. And we're going to mix until that one has disintegrated, and that one did not take long at all. Beautiful. Okay, and now these results are immediate, so we're going to take our scale here. Okay, and then here's our sample. So where do you think it belongs? Right. This is, oh, I'm upside down. Here you go. So that's 7 and that's 8. Okay. All right, and we're done with pH. Okay. All right, we're going to move along now to dissolved oxygen. Now for this one, I'm going to do both tests. I'm going to do both the in-person tab test, and then I'm also going to do the Winkler titration from the box. It takes a little bit longer, but it's going to be much more reliable results, okay? So here's the information for dissolved oxygen, and then here's the information. So we are going to fill this test tube to overflowing with the water sample, and we're going to add dissolved oxygen test tabs to the test tube. Now, this would be ideal if we were out in the field and we could completely submerge this tube. And I tried doing some videoing in the field, but I was having technology problems, so that's okay. So I'm rinsing the sample with water we got from the creek, again, to try to keep all of our sample valid. But this one has already had a lot of oxygen in it, so I'm going to use this tube that I filled up properly. If you notice, it has no air bubbles, right? It was even capped underneath the water. So this is a good sample. So I'm going to take this, see how it's got that meniscus there, right? So that's really, really good. And so I'm just going to try to fill this as much as I can. This data is probably going to be a little altered because of this, but we'll just see. Okay. All right, so we filled it overflowing, and we're going to take 2 of the dissolved oxygen tabs and put in there. I always like to do the tabs right over the sample place, just because they tend to break up on you, like that one did. And so that way, first off, it helps disintegrate faster, but then also you're not losing any money from your tab not being right. There we go. All right, we're going to cap it. We're going to try to make sure that there's no air bubbles in here. Looks pretty good. All right, and then we're going to mix it until they've disintegrated. So it says that disintegration can take about 4 minutes. So we'll just wait here. All right, while we're waiting, aquatic animals need dissolved oxygen to live. Fish, invertebrates, plants, aerobic bacteria all require oxygen for respiration. Oxygen dissolves readily into water from the atmosphere until the water is saturated. Once dissolved in the water, the oxygen diffuses very slowly, and distribution depends on the movement of the aerated water. Oxygen is also produced by aquatic plants, algae, and phytoplankton as a byproduct of photosynthesis. Aquatic organisms require different amounts of dissolved oxygen. Dissolved oxygen levels below 3 ppm are stressful to aquatic organisms. Dissolved oxygen levels below 2 or 1 ppm would not support fish. Below levels of 5 to 6 ppm are usually required for the growth and activity of aquatic organisms. Chemical oxygen demand, or the BOD, is a measure of the quality of dissolved oxygen used by bacteria as they break down organic wastes. It's like cellular respiration. In slow-moving and polluted waters, much of the available dissolved oxygen is consumed by bacteria, robbing other aquatic organisms of the dissolved oxygen they need to live. So, again, we took this sample from East Tennessee in November. There was quite a bit of detritus matter, or a bunch of dead and decaying leaves, but we did do a very small mini bioassay, and we discovered that there was quite a few crayfish, there was a mayfly, and there was a water beetle, and we saw 2 water bugs, so the ones that are on top, floating around. And so there was some organisms there. We did not see any fish, but it is November, and we also noted that it's been rather cold, but these last 2 days have been like 75 to 80, so that's why we decided to go out today. So all right, it looks like my tablets have nearly disintegrated. I'm going to try to speed up that process just a little bit. Okay. All right, and while that is processing for 5 minutes, we're going to go ahead and look at the Winkler titration. So for the Winkler titration, okay, this should have been submerged completely in water. And like I said, I don't know how this will work, but we're going to take, okay, so where this is overflowing, and then we are going to take our manganese sulfate and put in 8 drops. So 1, 2, 3, 4, 5, 6, 7, 8. I think it's so important for students to know how to do all the different methods. So that's why I want to teach you guys how to do this. And then 8 of our alkaline potassium iodide, azide, and 8 of those. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then we're going to place the cap and mix, and then watch the precipitant go through. All right, note, you should probably wear gloves with this. Definitely don't do as I do. All right, and we have to wait on that one, so while we're waiting, I'm going to clean these up. Again, if you're putting any chemicals down the sink, these are very small samples, that's fine, but let's run plenty of water to just ensure that we're not putting too much, kind of a dilution to the pollution here. So we don't want to cause any mishaps. If you think those samples were darker, timing really is important for water quality testing, because if the longer you leave something, sometimes the darker it gets or the lighter it gets. So if it says wait 5 minutes, you should try to be as accurate as possible. You don't want to just wait around too long for any of this, okay? All right, we're just waiting here. I'm cleaning up my lab like a good AP student. We do this lab in the spring, but this year we're doing it in the fall, right, for COVID, just in case I don't get to see these students in the spring, as well as the thought that we just completed watersheds, so we're talking about like, okay, well, if water is draining from certain areas, what would it look like? So if any teachers are out there, I get all of my stuff from Carolina. These were Lamont, but I had a grant for that. This is actually a very old dissolved oxygen kit, and I find that it works better than the newer one. So I don't know if there's any validity there with that. But I found success with that. I also enjoy the Carolina bag. I think that's really nice as well. And I haven't really found anything else. So if you know of something, please let me know. But that's what I know. All right, looks like our DO over here is coming along very well. All right, this hasn't precipitated enough yet. That needs to get down just a little bit lower. And I know that this piece will come next. So again, these things are kind of corrosive, so just be careful. But I need a gram of this. And this one's about done. So here is the dissolved oxygen levels. So remember, levels 5 to 6 are usually required for the growth and activity of aquatic organisms. All right. So hopefully you got that data. I think just another second. Again, going to run a lot of water. If we were in the field, we would just put that over with the vegetation, not straight in the water, so the plants can absorb any chemicals that could be there. Let nature take care of itself. Okay. Okay. So at this point, we're going to open it back up. And And we are now going to put the sulfamic acid powder in here. Oops. There you go. And at this point, the dissolved oxygen is is fixed. Okay. So you can kind of see now that it's getting all like black specks. Okay. Now we're going to take a titration tube. Oops, sorry, excuse me. Titration tube and fill it to the 20 ml line. So we're going to fill it to there with our solution. Okay. So 20 mils. All right, and then we're going to fill the titrator with sodium thiosulfate. So we're going to be like doctors, right? And I fill mine all the way up to 0. And then we're going to add 1 drop into the titration tube at a time, and then swirl in between each until this becomes a faint yellow. So 1 drop, swirl, 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 1 drop, swirl. Again, waiting for that faint yellow here. That looks good. Do 1 more for good luck. Yep. All right, so to me, that's a faint yellow. You can always put it on a white surface to see the difference. Let's see that pale yellow. Okay, so pale yellow. Might do 1 more. Pale. Okay, now we are going to remove this and use a pipette, or in this case, the actual starch indicator, and we're going to add 8 drops of this. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. All right. Let me get that nice, pretty blue color. Okay. And then we're going to titrate this sample until the blue disappears. Okay, so blue. So 1 drop, swirl, 1 drop, swirl, and it's done. So if I read this, okay, and I started at 0, let's see if we can focus in on that. Alright, looks like I'm going to have to help you out a little bit. So we started at 0, and our meniscus is now at 7. So how many parts per million would our water be? Basically, that difference will translate into parts per million. Alright, and then let's review the dissolved oxygen. So dissolved oxygen. You should have below 3 are stressful, 2 to 1 won't support fish, 5 to 6 are good for aquatic life. So I think in this example you can see a difference between Winkler and the official chemical test, as well as a difference in the sample tests. They'll get you into the ballpark, and like I said, there could be some error because I didn't submerge them. I used these samples that I gathered, but hopefully this has been helpful for those of you who can't be in person to do water quality testing, and I hope that this has been beneficial for anybody who's never done these tests before. Basically, I'm not going to lie, a lot of this stuff I'm just reading off of what the things tell me, the instructions tell me to, so it's not like I'm doing anything per se special or better than, it's not like I've memorized these. So if you guys have any questions or concerns or something, please let me know. And hopefully, as you gathered your data, you can now start chemically assessing how healthy that creek is. And so that's our ultimate goal, is to determine what kind of substances are there and would we consider these healthy or not healthy, okay, for the environment. So thank you so much for watching this video.